Now we discuss the topic plastic analysis of structure. This is fifth unit of essay, structural analysis. So first of plastic analysis introductions. So elastic analysis. So elastic analysis and plastic analysis. So elastic analysis is statically determined. It is analyzed by static columns. So statically indeterminates analyzed by statics and comparability. So based on the following assumptions, the stresses in material less than elastic limit, and then deflection are small. This is the elastic analysis. So next one is the plastic analysis. So a plastic is based on the finding the collapse load of the structure. This requires the knowledge of what happened at collapse and how the structures behave when the stresses in the materials exceed the elastic limit. So elastic is statically determinate and indeterminate. So determinate is static alone. So indeterminate is elastic and cable and compatibility. So and then the structures finding the collapse load of the structures. The structures a knowledge of what happens the collapse and how the structures behave. The stresses in the materials exceed the elastic limit. This is a model. We will develop the principles of the plastic theory, which are widely used to analyze and design of steel structures. So most of the following is used to the analysis under design of steel structures. So this is a stress strain curve, fundamental concept of the plastic behaviors, stress strain curve for the mild steel. So this is the starting point. This is a stress, and y direction is stress, and x direction is strain. The following the values of this plastic slope is 0, so 0 to 0.04. The next one is starting the points, and this is plastic limits, and this is a strain hardening. This is a failure stages. 0.2 and 0.2 limits is more than the failure stages. So this is the stress strain curve for the mild steel. So next one is the collapse of the structures. So any structure can be made to collapse by applying a load of sufficient magnitude. So the structure may collapse by a combination of elastic buckling, instability of one or more members, or the plastic collapse of the formation of the plastic hinges. So this is the plastic behavior of the beam. So simply supported beam, center point load is acted. So the bending moment is, this one is a bending moment. So elastic behavior. Mm, this is the cross section, shape of the material, any shape of the materials. This is neutral axis, summation C equal to summation T. Compression, this strain is the compression. This is tension forces, top portion, and the compression force, tension forces and the compression. This is the final origin of the sigma is equal to E region. Sigma T, the tension in the truss. This is the partial plastic. The beam is loaded further. The bending moment is formed. The neutral axis is formed to the strain and stress curve. And the fully plasticide, the shape is axis and the strain and the stress. This is the fully plasticity. So the moment is WL by 4 into MP, and WC equal to collapse load is 4 MP divided by L. So this is a collapse load formation. WC equal to lambda into WW. The collapse load. This is the plastic hinges formation. Fully plasticity. At this stage, the section has reached its full moment capacity, and there is no more stress capability available to develop any additional moment of resistance in this section. What do you think will happen to the beam? The beam will be collapse. This is the fully plasticity. So direct calculation of the plastic moment and the rectangular section. So this is rectangular section. Rectangular section. Breadth B and depth is D. So neutral axis rectangular cross section. So the neutral axis mention of the top portion and the compression is compression is top portion and tension is bottom portion. So, this is the formation of the fully plasticity. The shape formation of the fully plasticity. So sigma y is the top stresses formed to the sigma y, and compression forces stresses to the tension forces. So C equal to T. So 0.5 PD into sigma y. So ZP means plastic elastic section. So ZE is elastic modulus section. So plastic section of modulus, elastic section of modulus. So this is the rectangular section. So ZP is PD squared divided by 4. ZE is PD squared divided by 6. So MP moment, plastic moment is MP equal to C into D by 4 plus T into D by 4. So PD divided by 2 sigma y into D by 4 plus PD divided by 2 into sigma y into D by 4. So the plastic moment MP equal to PD square divided by 4 into sigma y. So PD square divided by 4 already find the section of modulus, plastic section of the modulus, PD square divided by 4. So PD square divided by 4, the values of ZP, sigma y. So MP equal to ZP into sigma y. This is the plastic moment of the section. So plastic moment MP equal to ZP into sigma y. Sigma y equal to yield stress, and ZP is the plastic section modulus. That is the plastic moment. So position of the neutral axis is the position of the neutral axis C equal to A1 into sigma y. So T equal to A2 into sigma y. So equilibrium of the cross section C equal to D. So A1 into sigma y equal to A2 into sigma y. What does this equation tell you? A1 equal to A2. The neutral axis is the axis of equal area. So sigma y cancel the values, same. So cancel the values sigma y. So A1 equal to A2. This is the neutral axis. So direct calculation. Direct calculation of the plastic moment I section. So this is the I section of the safe factor. Safe factor. What is meant by safe factor? Safe factor means plastic section modulus divided by elastic section modulus. So that is a safe factor. So direct calculation of the plastic moment I section. This is I section. So x direction and y direction cut the section. So breadth is B, depth is D, and then this is a fully plastic side. C1 to C2 is compression force. D3, D4 is a tension force. Sigma is a stress. So clear the moment of MP. So MP1 equal to C1 into T by 2 minus T by 2. C1 equal to PT into sigma y. So MP equal to MP1 plus MP2 plus MP3 plus MP4. So this is the fully plastic moment. MP1 equal to C1 into T by 2 minus T by 2. So C1 equal to PT into sigma y. So MP2 equal to C2 into T minus 2T divided by 4. So C2 equal to Z into T by 2 minus T into sigma y. So MP3 equal to T3 into D minus 2T divided by 4. T3 equal to Z into T by 2 minus T sigma y. So MP4 equal to T4 into T by 2 minus T by 2. So T per 4 equal to PT into sigma y. So the safe factor is 1.15 about x axis. Safe factor is 1.6 about y axis. So this is the safe factor of the I section. So next one is asymptotic section. Asymptotic section do not yield simultaneously at the top and the bottom of the section. The neutral axis moves as a yield spreads through the section from the centroid before yield to the axis that bisects the cross section area. Can you identify the position of the plastic neutral axis? That is 20 mm the above the basis. Calculate the fully plastic moment of the section. Take sigma y equal to 275 Newton per mm square. Asymptotic section, the continuation. So C equal to D, area into sigma y. So area is area values is 200 into 120, so 4000 4000 into 275. Sigma yield stress is 275 Newton per mm square. So substitute the values of sigma y into area. So 4000 into 275, 1100 kilonewton. So full plastic moment MP equal to C into 50 plus T into 10. So C is 1100 into 60 equal to 66 kilonewton per meter. So MP equal to sigma y sigma p into sigma MP into sigma y. So MP plastic moment, ZP is MP is a plastic moment, ZP is a plastic section modulus, and sigma y is a yield stress. So ZP plastic section modulus ZP equal to MP divided by sigma y. So already find out the values of the plastic moment, 66 kilonewton per meter, 66 kilonewton meter. So 66 into 10 power 6 divided by 275 equal to 240 into 10 power 3 mm power 3. So effect of axial force. So m dash p equal to so this is the rectangular section P into D. So this section cut by the section, compression and tension, the fully plasticide, yield stress is formed to the top and bottom portions. This is axial stress. This is bending stress. So the presence of the axial force reduces the plastic moment capacity. However, in low-rise structures, axial force are too small to have significant effect of MP. Sorry. MP then equal to MP minus PD squared divided by 4 sigma y into Z by D whole squared. So this is the effect of axial force. So this one is the effect of shear force. Shear force P into D cut by a section YY. So top portion and the bottom portion, or your direction of the cut the section. This is the parabola formation, tau y. This is bending stress and this is the shear stress. So MP dash equal to MP into MP minus P into Z squared divided by 3 into sigma y. So the shear force is reduced to the plastic moment of the capacity. However, they have the smaller reduction in MP. Their axial forces and need to be considered only when they are exponentially large. So this is the collapse mechanism, statically determinate and statically indeterminate. This formation of the one plastic hinges will reduce to the structures of the mechanism. So this is the plastic statically determinate. So simply supported beam examples. So this is the statically indeterminate structures. One end fixed and other end is hinged. So center pointers point load is acted. So two plastic hinges are required to form a mechanism. So fixed end is plastic hinges formation. So center pointers hinges formation to the two plastic hinges are required to be form a mechanism. So number of hinges for collapses n equal to r plus 1. So complete the collapse. This is n equal to r plus 1 complete the collapse. N less than r plus 1 partial collapse. N greater than 1 r plus 1. This is the over collapse. So n is the number of hinges n is a number of hinges. N is the number of hinges. R is the degree of redundancy. The structure is statically determinate. This is partial collapse. Structure is statically indeterminate. So we find out the number of hinges for the collapses. So this is the plastic moment of the structures. Thank you.